Have you ever looked up at the stars and wondered what mysteries lurk in the vastness of space? Among the most puzzling objects in the universe are supermassive black holes, vast regions of space where gravity is so intense that nothing, not even light, can escape. These cosmic giants, millions to billions of times the mass of our Sun, anchor galaxies and shape their evolution over cosmic timescales. But recent discoveries have revealed a surprising twist. Some of these supermassive black holes didn't just grow over billions of years. They appeared in the universe's infancy, just a few 100 million years after the Big Bang. To put the magnitude of this discovery into perspective, consider that the universe itself is about 13.8 billion years old. Observations show that some of the oldest black holes were already reaching monstrous sizes when the universe was less than a billion years old. A timeline that simply doesn't add up. For decades, astrophysicists have struggled to explain how these early black holes could have become so massive so quickly. Now, new research is shedding light on this cosmic mystery, and the results challenge some of the most fundamental principles of physics. Let's start with the basics. Black holes form when massive stars exhaust their fuel and collapse under their own gravity. Over time, these stellar mass black holes can grow larger by merging with other black holes or by consuming nearby gas, dust, and even stars. This process of growth is not random. It follows specific physical laws that govern how material falls into a black hole and how much energy is released in the process. As material spirals towards a black hole, it forms a glowing accretion disk where gravitational forces heat the matter to extreme temperatures, producing intense radiation. This radiation is so powerful that it creates a counterpressure that pushes against the material trying to fall into the black hole. This balance of forces is governed by a rule called the Eddington limit, named after the British astrophysicist Sir Arthur Eddington. The Eddington limit sets a theoretical upper limit on how fast a black hole can grow. If a black hole tries to feed too quickly, the radiation pressure will overwhelm gravity, stopping the accretion process and effectively starving the black hole. Given this constraint, the rapid growth of early supermassive black holes presents a paradox. According to our understanding, it should take billions of years for a black hole to grow to millions or billions of times the mass of the Sun. Yet astronomers have observed quasars, extremely bright objects powered by supermassive black holes, shining in the early universe less than 500 million years after the Big Bang. How could these black holes defy the Eddington limit and grow so large in such a short time? To answer this question, a team of researchers turned to two of the most powerful X-ray observatories in space: the European Space Agency's XMM-Newton and NASA's Chandra X-ray Observatory. These telescopes are uniquely suited to studying the high-energy environments around black holes, where matter reaches temperatures of millions of degrees. By analyzing 21 of the earliest known quasars, the researchers found compelling evidence that these ancient black holes grew through a process called super-Eddington accretion. Super-Eddington accretion occurs when a black hole consumes matter at rates that far exceed the theoretical limit set by the Eddington threshold. In this scenario, the black hole doesn't just grow, it devours its surroundings at an unprecedented rate, defying the conventional laws of physics. But how is this possible? To understand, we need to look at the unique conditions of the early universe. During the period known as the Cosmic Dawn, less than a billion years after the Big Bang, the universe was a dynamic and chaotic place. Galaxies were just beginning to form, and the first stars were igniting, flooding space with light. In this turbulent environment, black holes may have had access to vast reservoirs of gas and dust, providing an abundant supply of material for accretion. In contrast to the relatively stable conditions of the modern universe, the early cosmos may have allowed black holes to grow unchecked, at rates unimaginable today. X-ray data from the XMM-Newton and Chandra telescopes revealed a fascinating relationship between the temperature of the gas around these black holes and the speed of the powerful winds blowing away from them. Cooler gas was associated with faster winds, while hotter gas was associated with slower winds. This link suggests that during periods of rapid feeding, the black holes were surrounded by denser, cooler material which facilitated super-Eddington accretion. These winds, traveling at thousands of miles per second, are a vital piece of the puzzle. They act as a feedback mechanism, redistributing energy and matter in the surrounding environment. Understanding the interplay between these winds and the accretion process provides valuable insights into how black holes grow and how they affect their host galaxies. But the discovery of super-Eddington growth also raises new questions. For example, what triggered this rapid feeding phase in the first place? Did these early black holes form from the remains of the first stars known as population 3 stars, which were much larger and more massive than today's stars? Or did they form from the direct collapse of massive gas clouds, skipping the intermediate stages of growth altogether? One hypothesis is that the unique properties of the early universe created ideal conditions for the formation and growth of black holes. High densities of gas and dark matter may have allowed black holes to form with larger initial masses, giving them a head start in their race to become supermassive. In addition, the lack of heavy elements in the early universe may have changed the physics of accretion, making it more efficient. Another possibility is that early black holes were surrounded by special structures in their accretion disks that channeled material inwards more effectively. These structures may have prevented the radiation pressure from escaping, allowing the black hole to grow despite exceeding the Eddington limit. Such scenarios challenge our understanding of how black holes interact with their environment and could have profound implications for the study of cosmic evolution. The implications of these findings go far beyond the black holes themselves. Supermassive black holes play a central role in shaping the galaxies they inhabit. The winds and outflows generated during super-Eddington accretion can heat and disperse the surrounding gas, influencing the formation of stars and the growth of galaxies. By studying these processes in the early universe, scientists hope to unravel the complex interplay between black holes and their cosmic surroundings. This research also highlights the power of modern telescopes to probe the most distant and ancient objects in the universe. The data collected by XMM-Newton and Chandra is a major step forward in our quest to understand the origins of supermassive black holes. But this is just the beginning. Future observatories such as the James Webb Space Telescope will provide even more detailed observations of the early universe, potentially revealing new clues about the birth and growth of these cosmic titans. As we continue to push the boundaries of knowledge, one thing is clear: the universe is far more complex and dynamic than we ever imagined. The discovery of super-Eddington growth not only solves a long-standing mystery, but also opens up new avenues of exploration. It challenges our assumptions about the limits of physics and reminds us that the cosmos is a place of endless surprises. So the next time you look up at the night sky, remember that the light you see carries the stories of countless cosmic mysteries. Somewhere out there, a black hole is growing, defying the laws that govern the universe and holding the secrets of creation within its grasp.